Oh, let's get. All right. Let's see. I got 13 people here. Lucky 13. Fantastic. Anybody have any questions? Some more people just rolled in. Let me make it really clear right now. The section that I said was extra credit is not even listed on the homework sheet, right? The section that is extra credit is 3.9. So it's not even on the homework sheet. And you won't be able to do all of it unless you have a graphing calculator. So that's why I made it. Well, that's why I wasn't even on the curriculum in the first place, because I'm not requiring you guys to have that yet. Some of you guys might be taking 120. Is anybody going to take 120 after this? Or is everybody taking statistics after this? Do you guys know? Or you're all like, dude, let me just pass this and then I'll work. You got to have some kind of plan, though. If you pass, Vu, what were you going to say?
I was saying I am.
You're taking 160?
Yes.
Okay. Anybody taking 120? Did you even? All right. Okay, that's fine. So I could have made you guys have the TI calculator. You're going to need it anyway. All right, all right. So a few more people came in. Let me know if you have any questions from homework stuff or anything else. There's some more people. Yay. I'm going to pretend like I froze. And then you. All right, so no questions. All right. All right, so we'll get back into where we left off. If there's no questions, and I believe I want to finish up 3.10, and then we desperately need to get into chapter 4, believe it or not. Believe it or not, we're gonna do it. Where are you, 310? There you are. So does anyone remember what the last thing we were talking about was? I'm not saying I don't, by the way. Anybody?
Systems of equation.
Systems of equations, kick ass. Let me see. I want to do this up on the board. Screw this stuff. So the thing we left off with last time was we solved it graphically, and then we solved it using something called substitution, right? So the last thing we got to do, let me see. I'm going to show you. Well, let's see. Do they even talk about it? No. That's weird. Screw it. I'm going to show you another way to do it. They don't show you, it looks like. Yeah. All right. So let's do a problem. Let's do a graphical problem, a substitution problem, and then I'll show you a third way to do it, and then we'll get into chapter 4. Hold on. Let me move you guys over here. Sure. Let me find me again. Where am I? There I am. All right. So a system of equations. The amount of variables you have must equal the amount of equations you're given to have a chance of solving that system. And when you solve a system, it means you find all the values for all the variables. So for example, if I have, let's just make this to the point here. Let's see, you could do it, Jeff. 3, 2. Yeah, I like it. I think that should work. We'll find out if this works. Did Jeff make one that works? Okay. Can we graph these relatively quickly? So this first one, can somebody tell me one piece of information you know about this line? Anything?
The y-intercept is -4, 0, -4.
There you go. Somebody else give me another piece of information.
Slope is 2.
Slope is 2, kick ass. So what can I put on my graph right now for this equation? Where do I start?
The y-intercept.
Good. I got to start at a point I know is on the line, so 0, -4. And then the slope tells me to do what? Somebody else. Somebody in the rain. What's that?
2 over 1. That's my turtle tank.
Oh. All right. Like, so up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. That's roughly not bad for me. All right, good. Real quick, just to kind of reinforce this, what point is this right here?
Two zero.
Yeah, 2, 0. I like that. 2, 0. Yeah, yes, it is 2, 0. So if I put a 2 into the equation, what should I get out? I should get a 0 out. 2 times 2 is 4 minus 4 is 0. Check. So every time you graph a line, you can very quickly check. Just take one of the points you went through, put it in the equation. It's supposed to work. That's the whole idea of a line, is it's all the points that work in the equation. How do somebody hasn't spoken yet? So might be here for a while. Can you tell me anything about this line? Anybody? That has
The y-intercept is 0, 1.
0, 1, 11. Now somebody else. What's the slope? We might be here for a while. Anybody else? Anybody? Now's your time to shine. What's the slope? Anybody? Are you guys really out there? Are you all mic-less? Oh, I see somebody's chatting at me. Yes, okay. I'll accept that. All right. All your asses were saved by Wendy. Now, I just do the same thing. I start at the y-intercept, 0, 1, and then it tells me to go. What's this telling me to do? Up 1.
Over.
Over 3.
All right. So up 1, where am I? Here we go. Up 1, over 1, 2, 3. That's why you do many, many steps on each one, so you can easily identify it when they cross. What point did we just get through here? What point is this?
Three, 2.
So what does that mean? That's the solution. That's the answer. What does that answer mean? What's special about that point?
That's what the equations have in common.
Yeah, so that point should do what?
Intersect.
That's where the lines intersect, but the point, the x, y, should work
It'll work for both equations.
both. I love it. So when I put a 3 here, 1/3 of 3 is 1 plus 1 is 2. When I put a 3 here, twice 3 is 6 minus 4 is 2. Bam. It's the one point that works in both equations. I like it. Have you guys ever seen the movie Clue? Anybody? You really should watch the movie Clue, but it's based on the board game, believe it or not. and it's an incredible movie. But the idea is, one thing is, if you want to try to solve who's killing everybody, so there's a lot of murders happening in this mansion, you can look at each scene and figure out who isn't there. So this is like one scene, this guy wasn't there. This other scene, the same guy wasn't there. It's where he intersect. He solves both problems. I mean, so it's the idea behind this is the same as the idea behind collecting information and seeing how they work together. That's all we're doing. Just mathematically, algebraically, graphically. All right. So let's solve a system of equations algebraically. I'm going to resolve this. Here it goes. All right, nobody's yelling at me. Good. With substitution, this is the last thing we talked about last time. Holy crap, what did he do? Solve. Wow, Jeff. Let's do it over here. What do you got, buddy? Yeah, let's do this. What do you got, Jeff? Dude, now I got to make something that works. Shit. All right, let's do 2a. Yeah, I like it. Minus b equals. Let's see. I think that'll work. Well, wait. Make this, there you go. Okay. All right. Let's find out if Jeff has made a good problem. So I wanted to throw some different variables because the variables don't matter, right? It's like the points on whose line is it anyway. So the idea with this one is actually more directly about using the information I'm given. What does the first equation tell me? What do I know is true from the first equation?
B equals negative 4a.
Yeah, it's amazing. All you had to do to answer that question was read it. I love it. I know that B is negative 4a. So then I can rewrite this one as twice a minus b, but what's b? B is
Negative 4a.
That's crazy. So that's why it's called substitution. You substitute what you know for one variable into the other equation. So you're using both pieces of information at once. There you go. I like it. So so here minus and negative, of course, is plus. 2a plus 4a is 6a. Oh, look at that, Jeff. You did a great job. Thanks, Jeff. A is 1. And then b is negative 4 times a. So b is negative 4. So then the answer would be 1, negative 4. So if you want to make a point out of values of variables, it's always alphabetical order, unless they say otherwise. So this isn't x and y, this is a and b, but it would still be a comma b then. Is everybody with me? Just like x comma y, it's alphabetical order. All right, you guys doing okay out there? Okay. Oh, somebody left. Shoot, I guess not. So here's the new thing. Actually, let me let you guys try one of these. I'm going to erase all this. Shoot. So here, you guys solve this here. What is it, Jeff? Let's see. Let's do. Yeah. Let's do. Yeah. Yeah, that'll work. I really hope it will. Try to solve that. Good luck. Oh, it's all coming from over here. Okay. Oh. Apology accepted, Ian. Better late than never in this case. So let's see here. So if I go to rewrite this using this 4 times m, but m is negative 2n. That's all I'm doing. Is that all right?
Yes.
Thanks. And then I know that m is negative 2 times n. So I know m is negative 2. So then what would the answer be as a point?
1, -2.
No?
-2, 1.
Yeah. So unless it states otherwise, you put it in alphabetical order. That's all. Points are understood to be in alphabetical order unless the problem states otherwise. Cool. All right. So let's talk about this other way to do these algebraically. And by the way, if I were to graph these two lines, and that would be disgusting. I don't know if you guys can understand. If I try to solve this for m, I'm going to get a fraction for what would then be the m-intercept. It would be disgusting, right? So thank God we have an algebraic way to solve these. Let me erase this. Here we go. All right.
I have a question really quick. You said put them in alphabetical order.
Yep.
For -2 and then 1, but the first one was 1 and -4. I don't understand what, like.
No. So alphabetical order. So, yeah, the first one had an A and a B, so the point would be A, B, and the second one had an M and an N.
M, N. Okay.
Yeah.
Okay.
So it's not like you're thinking about positive, negative, or something.
Yeah.
Okay. Oh, what are you doing? All right. So this other process, I like this much better, to be honest. It doesn't really, it's not easy or anything. I just like it. It's more honest. Substitution is sort of like invasion of the body snatchers. They replace somebody with something else, right? If you've never seen Invasion of the Body Snatchers, the title kind of gives it away. But elimination is much more direct. It's much more in your face. It's not behind the scenes being sneaky. It's, I'm going to kill you. So that was a little creepy. Too bad. So if I had an equation like, what do you got, Jeff? X plus y equals 11. And I also knew that x minus y was 9. Watch what I can do. This is going to be a little freaky. I kind of hope it's freaky. It should be a little freaky. I'm just going to add these two equations together. So I get 2x, the y's cancel, 11 and 9 is 20. Does anyone have a problem with what I just did? On one level, you should. It's like, why should you be able to do that, what I just did? I don't know. So tell me this. If I add something to one side of an equation, what do I do to the other side?
Same thing.
Same thing. So the same exact thing must happen to both sides of an equation. So what did I add to 9 to get 20? I added 11, right? So I'm supposed to add 11 to this side also, right? Right? Of course I am. I have to. But what is 11? It is this. So if I add this to this and this to this, I am adding the same thing to both sides. So I don't want you just to accept this. I want you to realize why it fits within the rules we know already. It has to. We can't learn something that breaks a rule we learned earlier. We actually can't. So this doesn't break any rules. Yay. And what's nice about this, look at that equation. How do I get what y is now? I'm not done until I get all the variables. How do we get what y is?
Just plug that into one of the equations.
Yeah, either one. So I'm going to pick the one where y is not negative. So if I put a 10 in place of x and I subtract, I get y is 1. So 10 plus 1 is 11. 10 minus 1 is 9. Crazy sauce. And thankfully it's x, y again. That makes it easy. All right. That's pretty nice. Now, the reason that was easy on this problem is because, do you see how the y's just want to die? Do you see how they just want to die? They both have the same coefficient except different signs. So when I add them, they will die. So what happens if I have two equations where that's not the way it is? So for example, you can see why it's called elimination. I'm killing a letter. What's the problem with either of these? Too many damn letters. So let me just directly kill one of them, right? And again, if you don't like kill, you can use the word cancel. Variables are not exempt from cancel culture. So what about if I had this instead? You can do it, Jeff. What do you got, buddy? I don't know, man. Okay, let's make it work. Okay. All right, I like it. I like it a lot. I really want you guys to think, now that you know you are allowed to add two equations together. You could do that wherever it makes sense. Why wouldn't you want to just add these two together the way they are now? What would that do you any good?
You'll still have the variables.
Yeah, you'd still have both the freaking variables. The whole point of combining them is to kill one of those variables. If only there was a what here. Because these are opposite signs already, right? If only there was a what here?
A 2.
A freaking 2. So what do I do to this whole equation to make a 2 show up here?
Add 2 to both sides.
No.
Multiply by 2 by.
No. I think you said divide, but you're gonna multiply by 2, aren't you? If I multiply this by 2, what do I get? I get 6x minus 2y equals -2. Let's get out of there, Jeff. -4. There you go, buddy. So if I multiply all of this by 2, and if you have trouble remembering what you're doing, put a 2 there, put a 2 there. Am I allowed to do that? Of course I am. I can multiply both sides of an equation by anything. Has there ever been a reason we would do this before? No. But do you understand why we're doing it? What happens now with these two things? If I combine these equations,
Cancel.
they cancel. Let me bring this down here so it's closer together. So what do I get when I add these together? I get 7x. These go away. -4 plus 11, 7. X is 1. Do you guys see that idea? So if nothing will cancel, or we're not done yet, I know, but if nothing will cancel the way they are, you can multiply one or both of them by something that will make something cancel, like we just did. If only there was a 2. Okay, then double everything. Now there's a 2. Now these kill each other. Yay. And then how do I get y? You can use either one of these you want to get y, because they're both true. I'm going to use the first one. Looks nice. So x is 1. 1 plus 2y equals 11. Subtract 1. 2y is 10, so y is 5. Is that all right? So if I want to write that as a point, be the point 1, 5. And this is wrapping up 310. We are done with 310 now. We are donezo.
Why did the book did not show us this way?
I don't know.
This is a lot easier.
I like this way. This is my favorite way. And I, oh, well, we didn't write the book. So what can we do? We do it, we deal with it as we will. So if this helps you in the homework, you are allowed to use this method also. If you want to use this method instead on something, you're fine. Okay. All right, so you just got to get in that homework so you can tell me if you have any specific questions. I now want to get into chapter 4. So let's take a look at chapter 4. Chapter 4 is going to be, we'll find out. I don't know how you guys are going to feel about chapter 4. Where are you, chapter 4? Here we go. Get out of there. Bum, 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 bum. Get over there. There we go. All right. Chapter 4 is getting in some nifty stuff. So it's getting into the different ways, the different types of reasoning. So it's kind of a silly first question. What do you think the word reasoning means? That's kind of really wide open. But for example, yeah, this one's kind of freaky. I don't like that example. Barf, barf, barf. Barf, barf, barf. I don't like that example. Yeah, all right, here we go. So some of this is going to be non-mathematical. Some of this will be very mathematical. So we can make a conjecture, which is sort of like another, it's kind of an equivalent term to hypothesis. And this is really what people mean when they say an educated guess is a conjecture. So if somebody says something and you want to prove them wrong. So if I said, everyone who lives in LA likes the Lakers. What's your feeling on that? How would you prove I'm wrong? All you have to do is what?
Ask.
And what are you trying to find?
Someone who
That's
doesn't.
not true.
True. So you're trying to find somebody who doesn't
that
like
don't
the
like
Lakers.
the Lakers.
Yeah. All I need is one counter example and everything falls apart for me, right? If I say everybody loves season 8 of Game of Thrones, that one is very quickly debunked. But all you need is one counter example. All right. So number 4 says, every time it rains, my softball game gets canceled. The game was canceled last night. And the conjecture is it must have rained. A counterexample would be a situation that would show the conjecture is wrong. All right. And I know we're not suddenly going to become a law class. I'm not going to try to teach you how to talk to a jury. But it does feel like we're sort of going into these weird definitions of things related to jury cases and stuff. But can you give me a counterexample for that conjecture? What would be a reason the conjecture might be false?
The softball field was overran by gerbils.
Exactly. That's so weird. That's the exact thing. No, it's not the exact thing I was thinking, but that's perfect. That's all you need. It doesn't disprove it, right? But it does show that there's some other thing that could have happened. Is everybody with me? So it could have been anything. You could have said anything. There are too many people were sick because of all the bites they got from rabid gerbils on the field. So they had to call the game, right? I love it. You guys doing all right out there? Everybody's working on something. Maybe you're doing essays for another class. Okay. All right. So look at this. All right, I love this. Look at number 5. This is really freaky. This is actually really cool. Obviously I didn't look at these ahead of time. Do what it says. Just take a quick minute and do what it says. 5a, put a -3 in for x. So just wherever you see an x, put a negative.
Bluetooth mode.
Oh, really? Is it activated?
Bluetooth connected.
All right. I have no idea if you can hear that. You probably can't even hear that, can you? When the guy, anyway, I'm sorry. You guys are like, Jeff's insane. Let's all hope he grades us well. All right.
We can hear it. We can hear it.
Oh, you can hear it. Thank God. I've done that so many times. And then I'm like, they might not even be able to hear that dude. So what I'm saying here is put a -3 in. Now, can you guys see why this is a much quicker problem than anything? What's the only part of this problem that matters?
The first part,
Yeah, what is -3 + 3?
0.
0 times who cares?
Zero is
0.
powerful.
Done. 0 is powerful. That's right. And what happens for part B then?
The same thing.
Same thing, because now the second one is 0, right? So who cares times 0 is 0. So a conjecture somebody makes after doing these 2 specific examples, they are trying to generalize the 2 things they just did. And they're saying, oh, it looks like any number that I put in is going to make the result 0. Is that true? Somebody
No.
give me a, sorry, go ahead. I think you said no. That's right. Somebody give me a number for x. Don't you dare say 1/2. I saw you coming with that.
3.
3, okay. Why did I say 1/2? Because 1/2 would make this 0. Do you guys see that? Half of 2 is 1 minus 1 is 0. But if I use 3, I get 3 plus 3, 3 minus 7, 2 times 3 minus 1, which is not 0. I actually don't give a shit what the number is. I just know right away it's not 0. It's not 0 times not 0 times not 0 is not 0. You guys okay with that? I mean, if you want to know 6 times -4 times 5 is -120. But all it matters is it's not 0. That's all I needed to show for this conjecture to be wrong. Are you guys okay out there? So that was a more mathematical example. I like it. Do you guys remember what isosceles means?
Yeah, it's on the note on the right-hand side.
Oh, shit. Thank you, Viv. Somebody should have said, I believe a triangle is isosceles, Jeff, when exactly 2 sides have the same length. Wow. Good job, student. Anyway, I forget that they do that shit. All right. So these 2 sides are the same length. They're saying these 2 sides are the same length. They're saying these 2 sides. It looks like this one might be all 3. And of course, this is kind of stupid. Does that mean that every, well, holy shit. Oh, I see what they're saying. So this is definitely not going to be, anyway. So does that mean that every right triangle is isosceles? Yeah, hell no. What about this right triangle? That is definitely not isosceles. No way. All right, so that one's kind of a silly one, but really, it kind of was liking that they put the word isosceles, but then they told you what the hell it was. So, oh well, I don't know what the point of that was at all. Let me clear all my stuff here. Here we go. Bam. And now here gets some interesting stuff. Here we go. And by the way, they use a term here I don't think I've said yet. Inductive reasoning is basically looking for a pattern and applying it. There's no guarantee that the pattern we see is true. So inductive reasoning actually cannot prove anything. So look at number 7. This is kind of neat. These are called triangular numbers. Do you see how they created it? So you start with a single point, a dot, and then you add 2 dots, so you make a triangle. That's 3 total dots. And then you have to add 3 more dots, so that's 6 total dots. Can you make the next 2 triangles, the next 2 triangular numbers? Can you do that? Don't say anything out loud. Figure out what the next 2 are.
One thing,
Sure, go ahead.
I got 15 and 21.
Oh, let's see. How am I going to do this? Yeah, this will be 15. You don't even have to like draw it, do you? Thankfully. So
I
this
just
is
use the
1.
pattern in the numbers.
Yeah, 1 plus 2. This is 3 plus 3. This is 6 plus 4. So it seems to be the one before. How do I write this? 1 before plus n, where I'm talking about the nth one. So this is the first one, second one, third one, fourth one. So the 5th one will be 10 plus 5. And then the 6th one will be 15 plus 6. So then the 7th one would be 21 plus 7. Is everybody? So that's the most fundamental thing about mathematics. But thankfully, mathematics allows for more powerful things than inductive reasoning. It allows for deductive reasoning, which we're going to get to in a minute. That's how you prove something. Blah, blah, blah. Who cares? All right. This one's neat. All right. Can you guys look at that and see what the pattern is? What's the pattern on the outside? That's the easy one.
Counting up that one.
Freaking one, yeah. Now let's look inside here. There's a 2 here, there's a 3 there, there's a 4 there, there's a 6 there. Where the hell did those come from? Maybe somebody has seen this before, but right here, what's 1 plus 1? 2. What's 1 plus 2? 3. What's 3 plus 3? 6. Can you guys fill in the next 2 lines? I've already got this one started. I did all the hard work for you. Ugh. Right. So 1 plus 2 is 3. 3 plus 3 is 6. That's the idea. And you just keep going. It's kind of crazy. And I want to see if I can show you something. You might think to yourself, does this weird, freaky thing have a use? It has so many uses, it's insane. Blaise Pascal.
That's a cool name.
Totally, man. I mean, good Lord. I don't know of many math people throughout history have had a more nifty name than Blaise Pascal. I mean, come on. Hey, Blaise. Is that like Sting? Did he suddenly say, just call me Blaise?
I'm changing my son's name.
It's really unfortunate because he then names the triangle after his last name instead of his first.
It should have been the Blazing Triangle.
Blaise Triangle.
Yeah. Now, of course, you have to also consider the fact that he's French. So everything we're talking about doesn't mean shit because I don't know what the word blaze is in French.
Blase.
Blase. That's what it is. That's good. Blase. So what do you guys put right here?
5, 10, 10, 5.
Yeah, 5, because 1 plus 4 is 5, 4 and 6 is 10, 6 and 4 is 10, 4 and 1 is 5. And then this would be 1 and 5 is 6, 5 and 10 is 15, 10 and 10 is 20, 10 and 5 is 15, 5 and 5 is 6. Okay, and then you can keep going till you go insane. Now, could you please take a minute? Have we talked about this? Yeah, I'm pretty sure we talked about this. Have we talked about FOIL stuff yet? I'm almost certain you guys know how to do this, but let's do this together. X times X is X squared. X times 1 is X. 1 times X is X, and 1 times 1 is 1. So what do I get? I get X squared plus 2X plus 1. Read off the coefficients for me.
1, 2, 1.
So if I do, now watch this. I'm going to do this a little quickly. If I do X plus 1 times X plus 1 times X plus 1, that'll correspond to this row. So I already know what this is. I just did it, right? Just stay with me. Stay with me. Here we go. And now if I multiply this out, I get X cubed plus 2X squared. Why am I doing it that way? I have no idea. Plus X squared plus X plus 1. So you get X cubed plus 3X squared plus 3X plus 1. What are the coefficients? 1, 3, 3, 1. So if I had to do X plus 1 to the 11th power, I could just figure this triangle out till I get to the 11th row, and then I know what all the answers are. I know what all the coefficients are. That is nifty and lame at the same time, I know, but that is not the only use of this triangle. This triangle is insane. This triangle is trippy as hell. If you've never heard of Pascal's triangle, you might want to just, Google a couple things about it. It's neat. All right. Does anyone know Fibonacci sequence? Oh, that's even better. But there's a connection between Fibonacci and Pascal, and more than just having a really cool name. I mean, Fibonacci is pretty good. Fibonacci. You can make some Fibonaccios. All right, I'll stop. All right, now, I'm going to clear all these drawings away. They're going to go away. Bye, all you drawings. Bye. Okay. Do number 10. I'll do it with you. And then we're going to prove it using algebra. So pick any number you like, any number you want to. And multiply by A. You could do it, Jeff. And 40. Divide by 4. Subtract 10 from that. And then subtract your original number. Don't use my number. You guys use your own number. You guys with me? Everybody do this. Just do each step. If you do it carefully, you should get something interesting. Has anyone gotten a result yet? Somebody tell me what number you started with and what number you ended with. Anybody?
I started with a 9 and still ended with a 9.
Okay, that's freaky. Anybody else?
Yeah,
So when do you
same.
10?
I got 5.
All right. So what's a conjecture we feel we can make?
With this formula, I guess we could call it, you end up with the original number.
Yeah, so this process or algorithm or whatever the hell you call it, I'm with you. You will, whatever number you start with is the number you'll end with. Is what we've done proof of that?
No.
Hell no. Did anyone use the number 1.0729? I want somebody to go,
Yeah.
holy shit, gotcha. No, I know for a fact nobody did. I know that. It's a known thing. So maybe this process doesn't work for that number. So this is still called inductive reasoning. So we're inflating specific examples. So we need to prove this using something known as deductive reasoning, which is instead of starting with a bunch of examples, and each one of you guys was an example, and then we came together and tried to make a generalization out of it. Now that is not a bad way to do things, to get a feel for something, but it isn't proof of anything, right? So let's,
this is
the
like
next thing.
bottom up thinking.
Sorry?
Is it like bottom up thinking, or?
I think so, maybe. That sounds like, yes, okay, I'm with you. So inductive reasoning is inflating from specific little examples to a big idea, right? To a general. So that sort of sounds like what you could call bottom up thinking, yeah. Although bottom up thinking to me is more like what you do after a hard test. Bottoms up. All right, let me clear all this. So here we go. We're going to prove that stuff now. Here we go. So here's what deductive reasoning looks like. You start with everything. So if I had to pick a number, the way that I pick how do I pick every possible number? I use a variable, right? So if let's start with n. And then the first step is to multiply that by 8. So now I've got 8n. You guys with me? So instead of specific things trying to come together to make a generalization, we start with the generalization. Pick a number. Okay, I pick all of them. Holy shit, okay. That's what this represents, doesn't it? That's everything. That's all numbers. Now add 40. What do you get if you add 40 to the result?
Eight n plus 40.
Yes, nobody say 48n. No, because they're not like terms. 8n is the result from part 1, right? And then I add 40. So again, what I did was I started with -7. I did 8 times -7 and got -56. And then I added 40. So all we're doing is we're doing all the same steps we just did. We're just doing it to n. Oh shit, I'm not gonna be able to make it to the end here, am I? Divide this equation by 4. So it'd be 8n plus 40 over 4. What do you have to, it's saying be careful. It's both terms have to be divided by 4. So what's 8n divided by 4?
2n.
2n. And then what's 40 divided by 4?
10.
10. All right, let me stop. And again, with my specific number, I divided -16 by 4 and I got -4. And if I put a -7 in here, twice -7 is -14 plus 10 is -4. I'm at the same place I would have been. I don't know if you quite get the point I'm trying to make there. All right, I'm going to have to clear this, unfortunately, the way that this technology works. So we're at 2n plus 10 right now. I'm going to clear this. So let me write this again. Get in there. So we're at 2n plus 10, and that tells me to subtract 10. So now we're at 2n, and then it says subtract the original number. And there you go. So that is the proof. It does not matter what number you start with. When you follow this process, you will end up with that same number. So I know somewhere in your whole life, you've encountered, I know, add your birthday and subtract the number of cats you own, and then add 47, then you get number 2, and you're like, oh God, get away from me. This is how you prove what they've done. In fact, real quick, just in case anyone's curious, if you said, all right, somebody give me a number, now add 3 to what you got, now double what you got, now subtract 6, now cut that in half, all right, you end up with the same number. I mean, so you can make your own process, and you could actually make it end up with anything you want to. It's not magic. So it's just algebra. It's just algebraic manipulation. All right. So I'm going to clear all of that. So this is inductive reasoning. It's the powerful reasoning. That's why it's the more complicated one, because it's powerful. It proves things. Blah, 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 blah. Blah, 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 blah. I don't care about that. Justice is shaking hands. Let me show you another example. Let me see if you guys are cool with this. Somebody give me an even number. Hey, somebody give me an even number?
4.
4, great. And somebody give me an odd number.
7.
7. What's the result? What kind of number is the result?
Even.
Does that always work that way? So let's see what now. So if you give me another even number 2 and an odd number 11, holy shit, it's still even. If I wanted to prove this, let me see if you guys, oh man, this might, all right, well, let's find out. Here's the neat thing. Stay with me, stay with me. I might be pushing it a little too far, but what is a general way to write an even number? I can't just say n, because n could be 5.
2n.
2n. And now we're understanding that n is a natural number, meaning 1, 2, 3, 4, 5. You guys kind of with me? So that's every even number is 2n. What's every odd number? Oh, shit. All right, this is weird. Don't say 3 something, right? So think about it. Give me an odd number.
11.
11, crazy. Isn't that an even plus 1? That's one way to do it. I could have said an even minus 1, but you know, there's a different ways to write it. Isn't every odd number
Would it be
one more than some even number? Are you guys with me? So I can write this as, and again, this is probably pushing it a little too far, Jeff, 2m plus 1. And then if I distribute this, I'll get 4mn plus 2n, which is twice 2mn plus n. So it's twice something which is even. So that's the proof. That might be me pushing things a little too far. You're not going to have to do something like this yourself. Don't freak out. This is just Jeff showing you something freaky. So any situation you're in mathematically, if you want to prove it inductively, you have to figure out what's the most general way to write the situation I'm in. Because then that'll prove it. If I can make it work for that, then that means it must work for everything, right? All right, maybe. All right, I'm going to clear all these away. Okay. I don't like the shaking hands. Go away, shaking hands. Let's see. Oh, this is kind of silly. Blah, blah, blah. Okay, so let's take a look at what the homework is going to look like so we're not all freaking out. So there's stuff that looks familiar. In fact, I think I've shown you this pattern before. Do you guys remember what the pattern was with square numbers? What's the difference here?
3.
Here?
5.
7. This would be plus 9. There's always plus the next odd, right? I like it. Anyway, and you can actually, anyway, there's more you can do with that, but that's just neat to see. And then you got these pentagonal numbers. That's how you say that word, kids. Pentagonal. That kicks so much ass. Why do they call that? Because they make pentagons. Woohoo! And again, it's just, can you see the pattern? That's all it is. It's just, can you see the pattern? Let's see. Oh, I love it. Anyway, so that one's just follow what they do. So all of this is just either finding a pattern, and then they get into the stuff that we did earlier about like the baseball game and the rain and the Gophers or the gerbils. That's what it was. Every 8-legged creature is a spider. I mean, right? Is that necessarily true? Just find a counterexample for those. All right. That's enough of that. You guys feeling okay out there? So again, you just have to get into that and start doing it to see what it's like. For this, what we're about to get into in 4.2, we're starting to get into, so the whole point of this whole chapter, chapter 4, is living in a non-linear world. So chapter 4 is slowly going to get us into like quadratic stuff. Does anyone know the quadratic formula, for example? Anybody ever heard of that? Negative b plus or minus square root of b squared minus 4ac. Does any of that sound familiar? You're all like, you're just spitting numbers right now, Jeff. No? Okay. Yes? Maybe? All right. So this one is going to be about, does anyone know this Pythagorean Theorem? I don't think that's come up yet. Good old Pythagoras, the Greek dude that took credit for all of his followers doing all the work. Look it up, kids. It's a sad history sometimes. And I don't know why they have a quote from John Bon Jovi, the mathematical genius. Anyway, so we'll get into Pythagorean Theorem, which is starting to use squares and square roots. So we're going to have to know some roots and some squares for the next section. And then looking even more ahead, I want to show you where we're kind of headed towards. Get over there. Then we're going to go and do a little bit of real life stuff. And this is something I wish it was timed differently. It would have been nice to do this before the election, so we could have looked at polls and stuff. But we can still go back and look at them, and then we can even tell, were they within the error? So this is going to be neat. And whenever you look at a poll, did anybody pay any attention before the election at predictions of vote totals, right? So they would say candidate A is going to get 44% and candidate B is going to get 48%. But that didn't mean that either one was going to win, because there was an error at the bottom that would say error is plus or minus 4% or something. So this could have been 4% higher, and this could have been 4% lower. It could have actually been the opposite of what it says. You guys have noticed that ever? Have you guys ever noticed that?
Yeah.
Yes. Okay. So we're going to get into the baby steps into looking at how they determine error in a poll. I like it. Okay, that's pretty good for today, I think. Yeah, why not? Is that pretty good? You guys remember that this week is a little weird because we have a holiday on Wednesday. Wednesday is a holiday, and you said, let's put it right in the middle of the week. It'll be like a tiny little fall break. Yay. So we still meet tomorrow. Also, the quiz should be active now. Exactly, it's Veterans Day. Thank you. Free food for vets. Yes. Oh, yeah. So one day of the year we take care of our vets. That's kind of pathetic, but you know, I think we're starting to get a little better taking care of our vets. The quiz, of course, is up there, right? So it should be active now if you want to go and start that now. You have until, I gave you until tomorrow at 8:15. I'm hoping I can grade most everybody's before class tomorrow. But you have until tomorrow morning at 8:15. If you have a weird circumstance where that doesn't work, just let me know. Okay. Anybody want to hang out? You guys got any questions? Or otherwise you are free to leave.
Yeah, I just wanted to, you know, the new method that you showed us earlier?
Yes.
Okay, so I just wanted to try it out on it's a homework thing, but I mean, I already did it. I just want to see if how you would do it for page 439.
All right.
Problem B. I already did it, but I just want to see how that would work with. Can you do with that problem?
All right, let me catch up to you here. All right. So this is one about the exam scores?
Yeah.
Yeah?
Yeah, because it's because
I'm
you
with
have to
you.
divide by 2.
So tell me what your equations were.
My equation?
Sorry?
So test x plus test y divided by 2 gives you the average, right? Which is the nut, which is
Y
90.
divided by 2 is 90.
Right.
That's one equation.
And the other one is the range, which is x minus y, which is 12.
I like it. And of course, this one real quick, you can just double both sides, right?
Uh-huh. Okay.
So now let me write that underneath here. And do you see how that?
Yep. So
That
that
is-
works now.
That's perfect. Yeah.
Okay, that's how it works. Okay. All right.
All right.
Thank you.
You're welcome. Everybody else all right? What's up? You guys good? All right. I'm going to head out. See you guys.